Have you ever wondered what could happen if we combine AI and quantum computers? It's both exciting and scary. Quantum computers are incredibly powerful and can solve complex problems much faster than regular computers, but there's a catch. Renowned physicist Michio Kaku has discovered something terrifying, and it could lead to the extinction of humanity. Join us as we explore the world of quantum computers and AI, their revolutionary potential, and the shocking warning from Michio Kaku. Quantum computers are exceptional devices that revolutionize computing by operating on the principles of quantum mechanics. Unlike classical computers that use bits to store and process information, quantum computers utilize quantum bits, commonly called qubits. While classical bits can only be in two states, 0 or 1, qubits possess the incredible ability of superposition. This means that a qubit can exist in multiple states simultaneously, representing both 0 and 1 at the same time. This is not just a little advancement in the basis of computation. We are talking about a large leap that provides possibilities for solving highly complex problems that our modern computers are limited to. The power of quantum computers lies in their capacity for parallel computation. By exploring different states and possibilities simultaneously, they can potentially solve specific problems much faster than classical computers. Undoubtedly, there is a widespread debate about the use of this revolutionary system. At first, you could liken it to the regular developments we are making on classical computers, increasing the processing power of a single chip, but the argument here is quite different. The improvement comes from the basic unit of computing. Quantum bits outperform classical bits, leading to the wide gap between the processing power of quantum computers and conventional computer systems. Now let's walk through the history of this invention. Quantum computers have a rich history dating back to the early 1980s, when physicist Richard Feynman introduced the revolutionary concept of quantum computation. Feynman envisioned a new kind of computer that could leverage the principles of quantum mechanics to tackle complex problems, beyond the capabilities of classical machines. However, it wasn't until the 1990s that significant breakthroughs in this field began to emerge. Back in 1994, a mathematician named Peter Shor, working at Bell Labs, unveiled an algorithm that sent shock waves through the scientific community. This algorithm was a game changer for quantum computers because it had the incredible ability to efficiently factor large numbers. Now you might be wondering why factoring numbers is such a big deal. Well, it turns out that factoring plays a crucial role in many encryption methods used to protect sensitive information in our digital world today. Shor's algorithm opened up a whole new realm of possibilities and sparked both excitement and concerns among scientists. It showed how powerful quantum computers could be in breaking the encryption systems we rely on. So throughout the 1990s and early 2000s, researchers rolled up their sleeves and started exploring different ways to build practical quantum computers. One of the most promising approaches involved tinkering with individual atoms or ions to act as qubits, which are the building blocks of quantum computers and other fundamental units of information in quantum computing. In 2001, a group of scientists at IBM achieved a major breakthrough. They successfully demonstrated the concept of quantum computing by using nuclear magnetic resonance to control qubits. Think of it as a eureka moment in the world of science. This achievement showed that quantum computation was not just a wild idea, but something that could actually work. It lit a fire under researchers, pushing them to progress even more. As time went on, scientists made incredible strides in developing stronger and more reliable qubit systems. They explored different types of qubits like superconducting circuits and trapped ions, each with its own set of advantages and challenges. They were trying out different tools in a quantum toolbox to see which worked best. All these advancements paved the way for the construction of increasingly powerful quantum computers. The number of qubits kept growing, allowing for more complex calculations and simulations. Later in 2013, something great happened. Google and NASA joined forces to create a quantum computer called the D-Wave 2. Picture it as a high-tech powerhouse that was going to be housed at NASA's Ames Research Center. But guess what? A government shutdown came along and threw a wrench in the works. It disrupted the project and stopped the quantum computer from reaching its full potential. Why? Well, it had to do with worries about the potential risks that could come from using such an advanced computing system. Even though the computer was up and running, the shutdown put a halt to further progress and plans until NASA could get back on track. Fast forward to 2019, and Google was in the headlines again, blowing minds left and right. They achieved what's called quantum supremacy with their super-duper quantum processor called Sycamore. What does that mean? Well, they tackled a complex math problem that would have taken classical computers thousands of years to solve, and more interestingly, Google's team cracked it in the blink of an eye. This accomplishment showed just how incredibly powerful quantum computers can be for specific tasks. It got everyone excited and pumped up about the potential of this technology, which led to even more investment in the field. Then in 2020, IBM dropped a bombshell. They introduced the IBM Q System 1, the very first fully integrated quantum computer designed for commercial use. It was like the ultimate dream come true for making quantum computers accessible and practical in the real world. Just imagine having a quantum computer right at your fingertips, ready to tackle all sorts of mind-bending problems. All these advancements in quantum computing caught the attention of governments and industries worldwide. They couldn't resist the allure of this transformative technology, so they started pouring in big bucks to support quantum research initiatives. They even set up fancy-schmancy quantum research centers and labs that brought together smart folks from academia, industry, and government agencies. Although the discovery and full adoption of quantum computers are still in their infancy, there are theories that claim that quantum computers or perhaps systems that operate using the logic of quantum computing might have been in existence in our universe already. We are talking about black holes. According to modern scientists, the existence of extraterrestrial intelligent life is believed to be probable. One intriguing possibility is that they might be utilizing black holes as quantum computers, which could explain why we haven't detected their presence. This scenario is related to the Fermi paradox, which has puzzled astronomers and cosmologists for years. Despite the high likelihood of life existing elsewhere in the universe, we are yet to find widespread evidence of it. The Hart-Tipler conjecture offers an explanation for this paradox. If advanced extraterrestrial civilizations have emerged in our galaxy, we should observe signs of their activity throughout. This conjecture aims to address the question of why we have not encountered clear indications of extraterrestrial civilizations, despite the probabilities. In connection to this line of debate, Michio Kaku suggests the intriguing notion of an extraterrestrial superhighway beyond Earth, a laser-based network through which billions of alien beings may be traversing the galaxy. However, determining the existence of such a phenomenon requires us to question our technological capabilities. We currently lack the means to definitively prove or disprove the existence of this hypothetical superhighway, which could potentially be situated right outside the Earth's orbit. As quantum computing progresses, researchers are busy tackling the remaining technical challenges and striving to scale up quantum systems. The ultimate goal is to unleash the true power of quantum computers, enabling them to beat problems that classical machines find incredibly difficult. We're talking about highly sophisticated tasks like large-scale optimization, complex simulation, and supercharged machine learning. Since qubits act like they have a split personality, but in a good way, their superposition property allows quantum computers to perform parallel computations and explore multiple possibilities simultaneously. It's like having an army of tiny workers tackling different tasks all at once. But here's the catch: to make quantum computing a reality, we need to manipulate and control those qubits effectively. That's where various physical systems come into play. Think atoms, ions, superconducting circuits, or even photons. These systems are carefully crafted and engineered to preserve the delicate quantum states of qubits, allowing us to perform operations on them. When it comes to crunching numbers in the quantum world, we have something similar to classical logic gates called quantum gates. These gates are like the conductors of a quantum symphony. They dance and manipulate the quantum states of qubits to carry out specific computations. By applying a sequence of these gates to a group of qubits, we can run quantum algorithms and solve difficult problems. But there's more. Quantum computing has another edge characteristic: quantum entanglement. It's like the BFF mode for qubits. When qubits become entangled, their fates become intertwined regardless of how far apart they are. It's like they're in constant communication, no matter the physical distance. Einstein once called this spooky action at a distance. We like to think of it as a superpower. The beauty of entanglement is that it allows qubits within a quantum computer to establish intricate relationships. They can work together as a dream team, processing vast amounts of information simultaneously. This gives quantum computers additional potential to solve certain problems way faster than classical computers. It's like they have a turbo boost for computational tasks. So with qubits, superposition, gate, and entanglement on the side, the future of quantum computing looks bright. They have shown impressive performance in many areas where classical computers struggle. For example, they are wizards at complex optimization, super speedy at factorizing those big numbers, pros at simulating quantum systems, and even masters of advanced machine learning tasks. One cool application of quantum computers is in the realm of optimization. They can come to the rescue when it comes to solving real-world problems like figuring out the best routes, managing supply chains efficiently, or allocating resources smartly. It's like having a genius advisor who knows all the tricks to optimize things and make our lives easier. But hey, there's another side to the quantum coin. When it comes to cryptography, quantum computing has caused quite a stir. Many cryptographic systems rely on the difficulty of factoring large numbers to keep our digital secrets safe. But guess what? Quantum computers have this magic trick called Shor's algorithm that can potentially break those encryption methods wide open. It's like having a master locksmith who can pick even the trickiest locks. So now, researchers are on a mission to develop quantum-resistant cryptographic algorithms to keep our sensitive information secure in a world where quantum computers are flexing their muscles. And speaking of muscles, let's not forget the incredible potential of quantum computers in the field of simulation. They can tackle the mind-boggling complexity of simulating quantum systems, something that's a real headache for classical computers. This capability has huge implications for fields like material science and drug discovery. Imagine being able to accurately simulate and understand the behavior of molecules and materials at the quantum level. It could lead to groundbreaking discoveries and innovations that were previously out of reach. And don't get us started on machine learning. Quantum computers are like the turbocharged superheroes of this domain. They have the potential to revolutionize how we train and optimize machine learning models. By harnessing the power of quantum computing, we could supercharge our AI algorithms, making them even more powerful and efficient. It's like giving our machines an upgrade to help them learn and make predictions faster and more accurately. Despite these huge potential breakthroughs, quantum computing is not without its challenges. The delicate nature of qubits, the need for extreme precision in controlling and manipulating them, and the mitigation of noise and errors pose significant hurdles. Researchers are continuously working to improve quantum error correction techniques and build more robust and scalable quantum systems. As we move forward, quantum computing holds the promise to revolutionize industries such as cryptography, optimization, material science, and artificial intelligence. It is a field of immense potential and excitement, with the potential to transform our world in ways we can only begin to imagine. Despite all the potential breakthroughs and advantages, Michio Kaku, a leading theoretical physicist and futurist, has raised concerns about the potential risks of quantum computers. He suggests that they could be used for destructive purposes, such as breaking encryption codes and hacking into secure systems. In an interview with Big Think, Kaku warns that we could face a new kind of cyber warfare where quantum computers are used to launch devastating attacks. He also suggests that they could be used to create deadly new weapons or to develop superintelligent AI systems that could pose an existential threat to humanity. Although the remarkable potentials and capabilities of quantum computers are yet to be fully realized, there is growing concern among researchers and experts about the potential risks and dangers they could pose to society. While quantum computers have the potential to solve complex problems, they also have the potential to break encryption codes, rendering many of our current security measures obsolete. This could lead to an increase in cyberattacks and data breaches, posing a threat to national security and individual privacy. In addition to the risks posed by cyberattacks, there is also concern about the potential misuse of quantum computers by malicious actors. For example, quantum computers could be used to develop new forms of weapons or to conduct sophisticated financial fraud. These risks are not just theoretical, as there have already been reports of quantum hacking attempts by state-sponsored actors. Experts are calling for greater investment in quantum research and development and the establishment of international agreements and regulations to ensure that this technology is used for the benefit of society. To address the potential risks associated with quantum computing, experts are calling for greater investment in quantum research and development and the establishment of international agreements and regulations to ensure that this technology is used for the benefit of society. Michio Kaku emphasizes the need for responsible development and deployment of quantum computing technology to ensure that its benefits are maximized while minimizing its risks. Quantum computing is a rapidly evolving field with the potential to revolutionize our world. However, it also comes with significant risks and challenges that must be addressed. As Kaku and other experts have pointed out, it is crucial to approach this technology with caution and responsibility to ensure that it is used for the benefit of humanity.